So for today's talk, we have the pleasure of having Philippe Charron from Technion, who will talk to us about Pleijel's theorem for Schrödinger operators. So Philippe, the floor is yours.
All right, thank you, Jean, and thank you as well to the organizers of this seminar. It's always a pleasure to be there, and I hope it will be a pleasure for everyone to listen to this talk this week. The work that I will be describing today is I will basically be discussing a recent paper that we wrote with Corentin Léna from Neuchâtel. But more than that, I will discuss the history of the results that led us to this final theorem. So the whole subject is Pleijel's theorem for Schrödinger operators. So basically, Pleijel's theorem was a very classical result concerning the number of nodal domains for the Dirichlet Laplacian on a compact manifold. However, it turns out that the same idea that was used by Pleijel can be applied to sort of a broader class of problems, which we'll discuss today. Right, so here's our settings. So we're looking at the Schrödinger operator H, which is, I'm going to use a minus Laplacian so that we always have positive eigenvalues and stuff like that. And the eigenvalues are going to be lambda n for the nth eigenfunction, and we put them with multiplicity in increasing order. Now, in our setting in general, V is bounded from below in certain cases, and in other cases, V will be negative and bounded from above. So it sort of brings out two situations. So one of them is more like the quantum harmonic oscillator, which is V of x is norm of x squared. So bounded from below goes up to infinity. But we also deal with potentials type kind of like Coulomb, where V of x is 1 over or minus 1 over norm of x. So basically, it's two completely different cases, but in both cases, we only consider the discrete spectrum. And there is like, you have both the discrete spectrum on one side and the continuous spectrum on the other side, and we just deal with the discrete spectrum when you have continuous spectrum. If you don't, like for instance, the quantum harmonic oscillator only has discrete spectrum, we just deal with the discrete spectrum. So that's our setting. Now we say, okay, there's many things you can study about these eigenvalues, and we're going to actually count the number of nodal domains. So nodal domains being you take the nodal set, take it out, consider the number of connected components. So there's many results that have been sort of connected with upper bounds on the number of nodal domains. And the first one was by Coulomb. So the idea is the nth eigenvalue has at most n nodal domains. And the key idea is that if you have too many nodal domains, it allows you to create a space of test functions which has Rayleigh quotient bounded by your eigenvalue and has very high dimension. So it's kind of like if your nth eigenfunction had more than n nodal domains, you can construct at least n plus 1 eigen test functions which are orthogonal to Fn. So it sort of like pushes the index of the eigenvalue up. So it has to sort of catch up with itself. Now, in terms of actual direct bound, Pleijel was not a direct improvement, but it's an asymptotic improvement. So basically, it tells you that asymptotically, the number of nodal domains does not increase with as n, but increases as a gamma of d times n, when gamma of d is a constant which is strictly less than 1, and it has an error term, which is not very easy to control. There have been some results of trying to understand this little o here. But in general, because we're only looking asymptotically, we're just looking at this main term here. And so it says that asymptotically, Pleijels bound is better than Courant's bound. Now, in order to prove that, you use a completely different set of ideas. So first of all, instead of looking at lambda n, you just say, what if I had just some eigenvalue lambda? And I say, okay, what is the smallest possible size of any nodal domain on this for an eigenfunction? And you can control it in terms of lambda using Fabre-Cron's equality. And then what you do is that you say, well, I'm going to estimate the number of eigen values less than lambda, and then you divide. So basically you get a Weil's term at the bottom, you get a Fabre-Cron's term at the top, and then when you divide, you get this constant gamma of d. And if you're in a setting which has a nice Weil's law, then Pleijels theorem holds. Now later on, this result was generalized to manifolds with either Dirichlet boundary conditions or no boundary, no boundary. And the idea was that if you're looking locally, the metric is almost flat. So if you have some stability estimates for Fabre-Cron's inequality, then you can say, well, as lambda goes to infinity, well, because nodal domains can be, smaller and smaller, then they kind of look like small balls. So those stability estimates will end up giving you the exact same constant gamma d. And there was this third result, which actually there's one more that I did not mention. It was by Josip Wojtowicz in 2009, that if you were in dimension 2 and your boundary was piecewise analytic, then Pleijels theorem also holds with Neumann boundary conditions. And the idea was to count the number of points that touch the boundary. So basically, you can say there's nodal domains either they touch the boundary or they don't. And the number that do not touch the boundary, because it's nodal domains, then you have boundary conditions which are Dirichlet for each nodal domain. So you can use Fabre-Cron on each. And the ones that touch the boundary, if you show that it's little O of n, then you have the right constant in the end. So that was the idea. But then Corentin-Léna in 2016 used a method which was quite different and allowed him to prove Pleijels theorem for any C1 alpha boundary with Robin or Neumann boundary conditions. And the new idea that was introduced is that instead of looking at nodal domains that touch the boundary, the idea is, where is the L2 norm of F located on the nodal domain? Is it close to the boundary? Is it away from the boundary? If it's away from the boundary, you can cut it arbitrarily close to the boundary. And you won't add too much to the Rayleigh quotient. So you can control the size of each one of those. Now, if it's close to the boundary, you cut away from the boundary. So basically, you remove everything that's not the boundary. And then basically, what do you get? You get a nodal domain with part of its boundary condition is Neumann, part of it is Dirichlet. So what do? You straighten up the boundary, and then you reflect it across. And then what you show is that you cannot have too many of those as well, because you use Fabre-Cron on this reflected domain. So those are all sort of like incrementally more refined tools to understand it. And so that's basically the history for the Laplacian. Now, we're trying to get a grip on the behavior of nodal domains of H, but H is defined in Rd. All the results for the Laplacian are bounded on, or not bounded, they're defined on manifolds. And the idea is that you count the number of nodal domains and you say, for a given eigenvalue, I have the volume of my domain, the volume of n, and then you divide by the minimal size of each nodal domain. So that's what you get here. So if omega is a nodal domain, you have that its volume is bounded by some constant, which depends only on d, times lambda to the minus d over 2. Oops, sorry. And so if every nodal domain has its volume bounded from below, then the nodal count, which is mu of Fn, is less than the volume of m divided by the minimal volume of omega. And then what you do is that you control this lambda n using Weil's law. Now, when you try to go from a manifold to Rd, you have some problems just straight away. And the first one is that Rd has infinite volume. So the second step of dividing the volume of m divided by something, it trivially doesn't work because you're just going to get a trivial upper bound of infinity. So you need to find a way to go around this issue. The second one is that in here you have just lambda. And so every nodal domain has its volume bounded from below by the same constant for each nodal domain, the constant depending on lambda. But when you have a potential V, V affects if you have a nodal domain here or there, they won't have the same bound. So you need to treat V effectively. And the third one is that Weil's law is not always true. So, so all the methods that were constructed throughout the years are always to deal with these three issues. So here's the idea. So the reason why Pleijel's theorem should work, okay, like before we even start thinking about it, like should it work? You say, okay, Weil's law looks like this. It's the number of eigenvalues less than lambda is some Weil's constants here. Integral over Rd of lambda minus v to d over 2, and the positive part. Now, when you look at Faber-Cahn, the Rayleigh quotient gives you something like this. So when you looked at manifolds with the Laplacian, you had a constant times lambda to the minus d over 2. Now in here, you're going to have lambda minus v, and then you're looking at the infimum over the whole nodal domain to the minus d over 2. So if you were to count the number of nodal domains, you would say it's roughly equal to the integral over Rd of 1 over the volume. So basically, when you integrate, you're just going to get the sum over all omegas, roughly. And so the number here is going to be less than this because you're just plugging the second line into the third line. So what do you get? You get the exact same integral, integrals. You get the integral over Rd, lambda minus v, positive part, d over 2, and you have the same here. So when you divide, you would basically just get these two constants, and that's exactly the Pleijel's constant. So that's the heuristic. That's why it should morally work. Now we just need to, make this happen. The first step here is that here you have this infimum term, and here you have this lambda n minus v, right? But there's an infimum that's gone. So if you could say that, well, for any domain, the infimum of lambda minus v is kind of like just lambda minus v. Like it's lambda minus v is almost constant on a nodal domain. Then this would make a lot of sense. the fourth line here. So basically, most of the tools that we developed were ways to control how much lambda minus v will change inside a given nodal domain. Oops. I think I put it there. Okay, there you go. Now, when you look also at this estimate, I said that basically the number of nodal domains is the integral of 1 over the volume. But if you have unbounded domains, the volume is infinite, so you basically don't count them. So you need to treat those separately. You need to show that there's not too many unbounded domains. Now, second thing is, does Valor hold? Like, do you have the formula that I gave for Valor? Does it actually, apply here for some choices of v? And do you have exactly, what I just referred to earlier? The infimum times the volume is equal to the integral. If this is true, then we're in pretty good shape. Now, the first method that was developed to tackle these two ideas was from my master's thesis in 2015, and basically restricted to the study of the quantum harmonic oscillator, which has a few advantages. So the first one is that the spectrum is explicit, it's known, and the eigenfunctions are also explicitly known. Actually, they're not explicitly known completely because you have high multiplicity, so you know a complete basis, but you don't know all the eigenfunctions. And the eigenfunctions are just some polynomials times a Gaussian function. So the zero set is pretty much like exactly the zero set of a polynomial. And also, you can control the degrees of Fn. You pretty much know the degree of Fn in terms of n, right? Now, basically what you would want is that you would want to control how much v changes. So you can say, okay, what if I were to look at two different areas? Well, I can look at, well, if I'm inside a small area, that's fine. But if I go across a long area, I should basically cross a lot of concentric spheres. So from Moore's theory, what you get is that the number of nodal domains of a polynomial is kind of like the degree to the exponent of the space, so degree of Fn to the d. But if you restrict to a sphere, you should have degree of Fn to the d minus 1 over each sphere. That's made actually precise. Like there's a direct estimate that you can have with explicit constant, that big O here, and also here. But once we establish that, what we do is that we take this potential V and we cut it into layers. And because V is radial, the layers are just a bunch of spheres. And we can say, okay, we count the nodal domains in two ways. We count the nodal domains, so the ones that cross a nodal domain, so basically they have to cross some sphere, they have to cross between two layers, or the ones that are sort of sandwiched between two spheres. So if they're sandwiched between two spheres, we know that the minimum of lambda minus v to d over 2 and the maximum of lambda minus v to d over 2 are quite close. So we should know that the sum that we get on one side is kind of close to the integral for Val's law. Now all you need to do is that you need to show that if you take too many spheres, this big O of degree of Fn to d minus 1 term will grow faster than mu of Fn, the mu of Fn that you're trying to control. Now, if you don't let it grow fast enough, then you don't get as good a constant as Pleijel. So what you want is that you want to sort of fine-tune how you cut with these concentric layers. And there's a way to do it. For the quantum harmonic oscillator, there's a way of choosing the layers such that the big O term here never grows as fast as this, as mu of Fn, and that you can get enough spheres so that you can accurately control the sum in terms of the integral. So that's good. The second method, which was basically an extension of the first method, and the idea is that if you have V, which is radial, now V is not specified like the quantum harmonic oscillator. V is radial, but we give it some growing conditions, basically at infinity. Okay, but for any radial potential, there exists a basis of eigenfunctions such that over a sphere, it's a polynomial. So the restriction of Fn to a sphere. So whatever the radial part is, you don't really care because all you're going to count is the number of nodal domains that can cross some sphere. And so it's basically the number of nodal domains of the restriction of Fn on a sphere. So then you apply the same method, you cut with spheres, and the number of spheres is defined, you fine tune it in terms of V and the gradient of V. So if you have V that doesn't oscillate too much, then you can do it quite well. I think the bound that we gave was something like V is norm of x to the B, and gradient V is norm of x to the B minus 1, which is a more general result than the quantum harmonic oscillator because that's exactly what you have in that case. The conditions are met. Now, another interesting thing is that the same proof works when you have a negative potential. So the Coulomb potential is an example of that, but there's other you can restrict yourself to a slightly larger class of potentials. So basically, potential kind of looks like 1 over x to the minus 1 over x to the b, and b is between 0 and 2. There's reason why you cannot go over 2 and stuff like that, but the idea is that you want to have infinitely many eigenvalues under the essential spectrum. But if your singularity at 0 is too big, then you basically get sort of an infinite spectrum at minus infinity. Like basically all the eigenvalues sort of sink to minus infinity. So it doesn't really help you. But that's the idea. You cut into the spheres and you look at intersections. So it was basically the same idea that was used in Yosef's paper, where you would count the number of nodal domains that touch the boundary for Neumann eigenfunctions. But the thing is that it really, has some limitations, and the limitations come from what we assumed both the potential to be and the eigenfunctions to be. So when you have radial potentials, all the level sets are spheres, which is great geometrically, and also it's great because since you have polynomials on spheres is an algebraic equation on an algebraic variety. So everything is tackled really well with those methods. But as soon as you have not polynomials, like even if they're very close to a polynomial, you can basically not say anything without a ton of other prior assumptions of what you're studying. But in the general case, you have no direct bounds like the ones that we used before. Also, sorry, I didn't mention, but the second result was done with Bernard Elfire and Thomas Hoffmann-Ostenhoff. Just to clarify that. So we had these assumptions on the second article also that V was radially increasing because you basically want to control the variation between two layers. And if V is increasing, then you can sort of like just say it's this minus this. Also, it gives you a very nice Weil's law. But this is quite limiting because we would like to study things like the sum of a certain number of harmonic oscillators, for example, multi-atom potentials. So if you had a sum of multiple Coulomb potentials, which is physically of very nice interest. The methods that were developed were not good enough to tackle this because they really directly assume that you had all these three assumptions. So the idea of treating non-radial potentials was not clearly, it was not clear that you could deal with this idea with just the method that we already had. So all these ideas were made assuming that we could localize nodal domains. So we could basically look at concentric spheres, and we can just sort of sandwich them in between two spheres and control it that way. That also worked with unbounded nodal domains, because you can show that this layer where V is equal to lambda n, every nodal domain has to cross inside. Like, you cannot have a nodal domain which is outside, completely outside this region, which is called the classically allowed region for this very reason. So how can you localize without having this idea of cutting and showing that you don't intersect, or not too many times? So the method in itself is quite elegant once you see the intuition and once you see the final result that you want to get first. And so when you look at Corentin's article from 2016, instead of looking at eigenfunctions that touch the boundary, you looked at eigenfunctions which had their L2 norm restricted to any nodal domain, which when you localize to the boundary didn't change, or when you localize away from the boundary didn't change. And you know that basically the L2 norm has to be either left or right. It cannot be nowhere. So if you're able to localize somewhere, then you can apply the estimates that sort of apply there. So you really, really, really sort of localize by force. You just say, instead of looking, okay, is this one going from here to there? Oh, I'm just going to use some partition of unity, cut it, and saying, well, because I've used a partition of unity, I forced Dirichlet boundary conditions inside this partition on each element of the partition. And so on each element of the partition, the estimates that we want to use are much simpler. Okay. When Corentin did his method, basically showed that you cannot have too many nodal domains which are concentrated next to the boundary. Like, it's basically this little O of n that sort of hides next to the boundary. So we're going to do that as well for the Schrödinger operators. So basically what we're going to do is that we're going to take this eigenfunction Fn, multiply it by some element in a partition of unity, and then that's going to allow us to have simpler estimates on one side, but worse estimates on the other side. So the first thing that we win is that because the lambda minus v will not vary too much, the infimum of lambda minus v and the integral of lambda minus v will be very close. They'll be much closer because we restrict ourselves to a region where v doesn't change that much. So that's the first thing. The second thing is that it will allow us to deal with the classically forbidden region, because we said that every nodal domain has to cross this region, has to have some part in there. But if we look at the L2 mass, we don't know where it is, but actually during the proof, it really appears that it has to have a big part of its L2 norm inside this region, inside the V less than lambda, right? It cannot have like, basically if you look at just Agmont estimates, which tells you that as you get away from the classically allowed region, you decrease exponentially fast. So basically, when you're trying to localize outside of the classically allowed region, you're never going to catch up. You're always losing too much because the eigenfunction is like localized on the partition of unity that you have. It's always localized on the side that's closest to the region v less than lambda. So it's kind of like a nice sort of moral equivalent to the Agamemnon's results, which tell you that, well, it has to decrease very fast away from the region that you're dealing with. So you cannot localize. Like if you were able to localize nicely, then you would have a contradiction, because you have that the Laplacian is positive and not negative. But you have this Faber-Kronig inequality, which gives you a lower bound on the lambda 1. So that's a nice feature. And also, if you have singularities, you can literally just single them out. Like you can just cut around the singularity and just deal with the singularity in one way and the rest in another way. So that's the advantages of using a partition of unity to study Schrödinger eigenfunctions. Now, what do we lose? So basically, when we cut, every time we cut, we add nodal domains. There's no way to go around it. Now, how many we add, that's another matter, but we know for sure that it's not going to be perfectly optimal, but if it gives you the same constant at infinity, then it's fine. Now, the second thing is that when you're going to deal with the Rayleigh quotient of Fn times the partition of unity, you're going to have a different Rayleigh quotient than just the Rayleigh quotient of Fn on a nodal domain, which we know already because because it has Dirichlet boundary conditions. And the third thing, which also we need to watch out for, is that when we looked at Pleijel's theorem, the idea was to divide the volume of M with the minimal volume of each nodal domain. Now, if we take a partition of unity, which has a lot of overlap, then we've increased the volume by some constant. And so that's going to directly mess up with our constant in the end. So we need to have a partition of unity that doesn't have too much overlap. Okay. Now, so this is the only technical part of the talk. So maybe I think a couple of slides. So the idea is that when you look at the Rayleigh quotient over this omega I. So omega I is, I pick an element in the partition, so AI. And then I look at I restrict myself to omega, which I cut with this localizing function here. And I look at the gradient divided by the L2. Okay. Now, because it has boundary conditions on omega, because either this is 0 or this is 0, then you use just the divergent theorem and you get this. So you have lambda n minus v times ai squared fn squared plus gradient of ai squared times fn. Now, the left-hand term is great because if you have ai, which is sort of like has very small support, then this here will be controlled very well. However, the right-hand side will grow because basically if you cut something very aggressively, then this norm will decrease, the denominator will decrease, but this will actually increase because the gradient will increase. So you need to control it in two ways. The first one is that you want to, if you can know the size of your partition, then you can control the gradient part here, which is good. But the second part is that you want to control this ratio, so the integral of fn squared divided by the integral of ai squared fn squared. And the way to see it is that if you cut fn with your partition of unity, and each point is covered by at most m elements, then you know that at least one index I, you'll have this relationship. So basically, because each x is covered m times, basically you cannot have like, so the sum of ai squared will be strictly, more than one. So I don't know if that makes sense or not, but the idea is that if you cover it at most m times, there's at least one moment where if you localize this AI squared, you don't mess up with the L2 norm too much. So you cannot have this decrease to 0 or arbitrarily flat. There has to be at least one index such that this ratio is not, well, this ratio on the right is not too big. It's bounded by m. And we say that omega is m localized in the support of AI. So the idea is that we're only going to count for each AI, we're going to count the number of nodal domains which are m localized in AI. And we're going to keep m fixed so that in the end, m doesn't mess with our estimates. So the idea that the way that you should see it is that if you have a bunch of cubes and you have overlap just between two adjacent cubes in dimension d, the overlap, the number of AI such that the support of AI includes x is less than 2 to the d. And it's pretty much the partitions we're going to use. All right. So I'm just going to go slowly on this one. So what do you have? You have that the Rayleigh quotient, we had lambda minus v times, the integral of lambda minus v times fn ai divided by the integral of fn ai. So this part divides. So you're just left with supremum of lambda minus v. Then you had m times the supremum of this guy. So I just put it all into one equation. Now, what you have is that because on this lambda, which you cut with AI, you can apply Fabre-Cron. So what it tells you is that the volume of omega that's inside the support is less than some constant, which I'm not going to put explicitly, but it's the Fabre-Cron's constant, times the Rayleigh quotient to the minus d over 2. So then again, what you obtain at the end is that the number of nodal domains which are m localized in one element of the partition is bounded by this. It's the volume of the region divided by the minimal volume of each nodal domain inside. So omega intersect with the support of AI. So what it tells you is that we're not going to apply Fabre-Cron to the whole nodal domain. We're just going to apply Fabre-Cron to each part where the L2 norm is high independently. So we would assume that we overcount quite a bit. Like we would assume that maybe every nodal domain can have its L2 norm, localized in 5 or 6 different regions. And so we overcounted 5 or 6 times, which might be very true. But we don't have a meaningful way to control the overcount that we have. All we have is this last part, but that's going to be enough. And now all that's left to do is that we choose a partition and then we try to control everything. But choosing a partition is not a very obvious thing. But if we have the right intuition, it gives you sort of a nice starting point. So from sort of micro-local analysis ideas, we know that if we want to look at what's happening around a point, we can localize up to radius lambda to the minus 1/2. So in our case, it's lambda n minus v to the minus 1/2 at this point. However, we need to understand that because v varies, and it actually can vary quite a bit, we need to give enough bounds on both v and the gradient of v so that basically we can localize, and as we localize, it doesn't change too much inside of a small ball, so that we need to relocalize up again. So we give the following conditions, which are quite broad. So at first we keep them very broad. So we assume just that v is between 2 powers of the norm of x. And if you remember, in the last result that I presented with Bernard and Thomas, we had this assumption that v of x was actually bounded above and below by the same exponent. So it was a and a here, and then you have c was equal to a minus 1. So this, we keep it much more open. And we see actually in our methods, we keep it very open until the very end. So it makes the calculation a little bit more messy. But the idea was that the method was powerful enough so that we could keep it separate the whole way and still get a meaningful result. Now, in here we have lambda n to the minus 1/2. We're going to assume that we can partition with, basically we take zd, take all these cubes, and then we make a partition of unity with an overlap of size delta, and then we rescale everything to size lambda to the minus n. The idea of leaving this overlap, which is finite but small, is that we're going to get a result which is dependent on delta, but we are going to allow ourselves to let delta go to 0 at the end, because we're going to get estimates which are sort of, there's a constant that depends on delta, but the rest will not depend on delta. And also we keep m open as well, and the idea is that we're going to pick m such that all of our error terms that we obtained during the calculations will sort of even out in the end. But in the proof, just to give you the primer on this, all the error terms that we get are optimized by c over 3a. Which again, if you have v can change by lambda to the c over 3a, so that's the radius, or lambda to the minus c over 3a, but the gradient is x to the c, so you divide, so you multiply it by c, and so you get something which is like, if it compounds too quickly, then you'll never get something something good enough. So you need to have something which is already quite small, such that even if, let's say, c is bigger than a, then it doesn't compound. So the main theorem that we get for the positive case, so we assume things that I just said. So v is sandwiched between two powers of norm of x, so a and b, and gradient of v is less than x to the c, and we have this weird condition here. So d over a minus d over b is less than 1/2 minus c over 3a. Now, why do we get this exactly? Now, if for example, if you had this thing here, which was not respected, does Pleijel theorem still apply? Maybe. Our result is not a if and only if. It would be actually quite interesting to know what the sort of like, when does a Pleijel theorem break down? Which is also an interesting question in itself. But the condition that we get here, I'm going to keep it like this just for a minute, just to say that basically when a and b are close, so this goes to 0. So basically c over 3a is smaller than 1/2. So the bigger this difference is, the more restrictions you have on c. So if you make a and b close together, you have a lot of latitude with c. If you make a and b far away from each other, then c becomes more restricted. But it's really hard to decouple those two things, except if a is equal to b, which I'll come up in a minute. So so now the theorem, instead of having this Pleijel bound, we get the Pleijel bound, which is gamma of d, times this constant 1 plus 2 delta over d, which is exactly the volume of a scaled cube. So I said we take cube, or we take any cube of like in ZD, and we thicken it by delta. So basically the new diameter is 1 plus 2 delta. And so the ratio of overlap is exactly 1 plus 2 delta to the d. Now, the cool thing is that these estimates, except for this little part, does not depend on delta. Everything else is constants which can be sort of taken away from delta. So you just have this term here, which does not play with everything else. So at the end, we can take delta to be the limit as delta tends to 0, and then we get exactly Pleijels constant. I'm sure it's possible to actually define partitions such that the overlap decreases over time. But we chose this method because it worked and it made everything more simple once you sort of took delta out of the equations. But I'll come back to that in a minute. Now, I said the easiest conditions for these guys was when A equal to B, like for instance, the quantum harmonic oscillator, where A is equal to B equal 2. Then C, now you get something a little bit strange. So C can actually be bigger than A. For the quantum harmonic oscillator, we have C, which is exactly A minus 1. So C is 1, oops, and A is 2. But actually, we can have perturbations which are bigger order than the potential, which is quite surprising because you would assume that you would need a potential not to oscillate too fast, such that the estimates of supremum, infimum, and integral don't change too much. But the way that we were able to localize is strong enough that we can really deal with very strong oscillations by localizing finely enough. So that's the result we get for positive potentials. Now, I told you we had this result for Coulomb potential. Now we get a similar result, which I'll go in detail just slowly. So how much time do I have? Great. So instead of looking at a radial potential, we allow any potential. And also we sandwich it between two orders of x, so x to the minus a, x to the minus b. And again, gradient is bounded by x to the minus. Now, we assume again this nice, weird looking condition. Oops. Oh, sorry. Actually, sorry, I made a mistake. So the condition is actually the second one, but you basically get the idea that because we flipped the signs, it's d over b minus d over a here. So the first one is not true. It's the second one that's true. Now, also, we allow a certain number of points which are singularities. So basically, at points xi, you have that the potential is kind of like x to the minus xi to the minus ai, and ai is anything from 0 to 2. Now, what we show in our method is that if we take a partition and then we just add these little sort of like, we add these little cubes around the singularities, you can control singularities independently of lambda. So you can say that the number of nodal domains which are closed in a fixed sense of any singularity is also fixed. So basically singularities, you can add any finite number of them, and at infinity won't give you anything because each singularity which of order less than 2 will only give you finitely nodal domains. It also gives you finitely eigenvalues, finitely many eigenvalues. So that's also the intuition why it should work. And then we have the same results. So if you're below the essential spectrum, you have Pleijels theorem with this constant, which is multiplied by 1 plus 2 delta over d to the d, which is exactly the same method. And if a equals b, then any c over 3 over a, 3 over 2. Also, again, because we're dealing with negative exponents, we have a positive inequality here instead of a reverse inequality on the other side. So it was c less than 3 a over 2, now it's c more than 3 over 2. So when you look at Coulomb potentials, or sums of Coulomb potentials, you have v of x, the a is equal to b is equal to 1, and c is equal to minus 2. So c is greater than 3 over 2, so that's great. And you have if you take any linear combinations of Coulomb potentials, you have a bunch of singularities of order 1, which is great. And then Pleijel theorem holds really well. So that's the result. Now, in this case, the partition is a little bit more tricky, because if you take a partition that is of fixed size for each element of the partition, what you realize is that at infinity, basically the nodal domains get bigger and bigger. Like they never sort of, because lambda will never sort of dominate V at any point, it basically says that even if you take lambda n to be, or n to be very large, any nodal domain has to have a small but fixed volume. Like it cannot decrease too much. So if you cut it with something which is the number of cubes that you add is huge, the number of elements in your partition is huge, then that will dominate. Like you add too many. So in this case, you cannot efficiently use cubes of the same size. So you need to have sort of a partition custom made so that you control the overlap, you control the number of times each point is covered, and you can fine tune the size as you go to infinity. So that's the difference in the method. I won't go into details on how it's done, but it really works in this setting. Now I've got a couple of interesting inquiries to finish the talk. So in our cases, we looked at the potential, and then we had this sort of intuition on how we could build a partition, but there was not a way to take any V, and without any assumptions on V, here's a way that you construct a partition. Here's a way that you can sort of just control it, because the overlap problem is there. So you need to have a way to both create a partition such that the size is right, but also the overlap is right with general V. So we couldn't find anyone that gave such a recipe to control, to construct partitions that had different properties. If someone could, for any V, have a method to construct the partition, then you could basically just apply the whole method directly without having to sort of specify what you're doing. So that would be an interesting thing to deal with potentials which are not included in our theorems. The second one is quite obvious as well. Pleijel was generalized from domains to manifolds. So can we do the same thing in RT? And the third one is, so far we've proved Pleijels theorem, but we have not proved that Pleijels theorem does not hold. Like we know that Weil's law does not hold, but we don't even know if Pleijel would hold for these potentials. Like we know that Weil's law doesn't work, but maybe for the nodal count for this this potential would still obey Pleijels bound. Like we don't even know. So that would be quite an interesting question on, can you make it break down? And so that concludes my talk. Thank you everyone.
Thank you, merci Philippe. We
have
time for questions now, so please just unmute yourself or write in the chat and we'll relay the questions to the speaker.
Yep. Can I ask a question, please?
Yes,
so for the growing potential, my intuition would be that the eigenfunction doesn't oscillate in the classically forbidden region.
Yes.
So then the fact that you require a bound on the growth, upper bound, is a little bit counterintuitive, because if it grows faster, then it just squeezes the number of nodal domains further.
Yes. So so usually the faster V grows,
yes,
you're good to go. That's fine. But what you would not like to have is, like, let's say a potential which is like increases very slowly, but has these oscillations that oscillate very fast. Because every time you go up a little bit, you get these sort of new ripples where your classically allowed region sort of increases both in size, but in topological complexity as well, and increases very fast.
Yeah. So this is C. You're controlling this with C, right? With the
So that's the rate
if you scroll the slides to the result, it would help us, I think. The first main theorem. Yeah, this one.
Yeah.
So the question is like, why? I know it comes with a proof, and the proof is very good, by the way. And B, like as you said, it's not a necessary condition, but having this B bound is strange. Like if it grows, if you control C and control A, you shouldn't have to control B. That's
yeah, you're right. Like usually, okay. So basically, what you have is that, like, because you're dividing by the Wiles term, if B grows very fast, then your Wiles term gets smaller. Like you're right. The more, like, the faster V grows, the slower the number of eigenvalues grows. So it's basically like n over 2 plus n over d, or n over b, sorry. Like that's the lower bound for the Wiles term. So basically, if b grows too fast, then your Wiles term can be very small. So your ratio is very high.
Okay, right. So my intuition is wrong. Yes, the number of oscillations is small, but also the number of eigenvalues is small, and then it cancels each other. Okay.
But here's the thing: you would assume that because you get the same thing at the numerator and the denominator, like it shouldn't matter. Basically, like heuristically, it should not really matter, because where you have a lot of eigenvalues, you also have a lot of null domains. So it should sort of cancel each other out.
Okay. Thank you. But yeah, well done. Excellent results.
Thank you.
Thank you for the question and for the answer. Do we have we have a question in the chat from Bernard Elfer. He's asking, what about potential that is x1 square times x2 square? You can maybe explain your question if you want,
yes,
Bernard.
Yes, hearing the talk, so I read the paper already, but you can think, you were speaking about exotic example, but the first thing maybe should be to analyze the model I write, like minus Laplacian plus x1 squared, x2 squared. So this model was proposed by Barry Simon a long time ago, and there are a lot of extensions for this. So this gives you, this is an example where V does not tend to infinity, but you have compact resolvent. And in some of the, so there are results about the spectral theory for this model, and there are partition of unity behind some of the proofs. So it's a natural question in this case. So you don't have the Weil formula, but do we have a Pleijels statement for this model?
Yeah, that's right. Like that's one of the exotic cases that is one of the first ones that popped into my mind, because that's one where sort of you don't have Weil's law, but you have a nice, compactness and discrete spectrum and stuff like that. So it's nicely algebraic in nature. Like it doesn't involve these crazy functions, so it should be easier to deal with. But I have not taken time to look at it.
So that's just to mention a question. If you look to the some of the way to prove the compact resolvent, you introduce partition of unity adapted to V, and the point is that the region where V does not tend to infinity is very tiny. So, x1 square, x2 square less than. So maybe the method that you propose has enough flexibility to to analyze this kind of thing.
Yeah, sure. Exactly. I think that it would be like it's very interesting that also the way that we cannot find a nice sort of direct Weil's law with the conditions that we had on the potential. So that the conditions in the middle of my slide, so d over a minus d over b, blah blah blah. So these also come from just Dirichlet-Neumann bracketing.
Yes, but you can imagine to have your proof without to use Weil, but only counting some boxes without to have to directly to use the Weil's as asymptotic.
Yeah, but we sort of cook up the Weil's asymptotic.
Yes, exactly.
With some partition of unity. So
this gives some hope to treat other cases.
So yeah, when you have two methods which are similar like that, there should be some way to make it work.
Thank you. Are there any other questions or comments for Philippe?
I have a couple questions.
Go ahead, Steve.
I'm trying to recall something from approximately 5 years ago, and I may not be remembering it very well. But Boris Hanen and I studied the nodal domains for random harmonic oscillator eigenfunctions.
Mm-hmm.
And my recollection is that there's some of the nodal domains, you know, think about the nodal domains which go into the forbidden region. Some of these nodal domains stretch out to infinity. They look like long, long fingers. And other nodal domains, if I remember correctly, and I think this is just visible from computer graphics, I'm not sure there are any rigorous results. Some of them look compact. They are in both inside and outside. They contain points in the forbidden region. Mm-hmm. They cross the boundary. But my recollection from the pictures is that there are some which are compact and others which extend all the way out to infinity. Mm-hmm. Okay, but I don't know what is the relative proportion of each of these things. If you're counting nodal domains, it might be interesting to count like how many there are of each type.
Yeah, actually, some of the pictures I seem to remember, because most of the pictures were, I think, done by one or two people that, and then sort of.
Bees and is a guy named Eric Heller, physicist named Eric Heller, and student Bees.
I seem to remember there was only like maybe two nodal domains that were unbounded in infinity. Like you had all these sort of little egg-looking.
Well, 2 is not a sacred
had, like,
number.
very
No, it doesn't work like that because 2 is not really a sacred number. Like if you just take a product eigenfunction, you can get these. You get these rectangular things going out to infinity, and you can look at the pictures. You know, it's like there's a lot of interesting things in the pictures that, to my knowledge, have never been established rigorously, unless I've not really kept up with it. But that's something I was kind of wondering about. So you're not aware of rigorous results that like count these numbers?
No.
Yeah, I have one of our collaborators named Peng Zhou. He generated 100 different pictures of these nodal domains. I think some of them may have made it into these published articles, and some of them we didn't publish. But you know, there are a lot of interesting details which I don't think are understood. Another one, it goes like this. You know, there's some famous papers by Nazarov and Soden about the nodal sets. You know, the expected number of nodal sets of random trickle harmonics. And generally speaking, every result you prove about the Laplace operator can be proved in the allowed region, but doesn't work in the same way in the forbidden region. And I'm wondering, I had the feeling somebody generalized Nazarov and Soden's proof to cases like Schrödinger operators or the harmonic oscillator, but I can't track down any references.
Yeah, also I think in the radial part, you have this decomposition where you have radial times spherical. So spherical harmonics averaged out should
No, I mean, because you're going to get different answers in the allowed and forbidden region. You know, the Nazarov and Soden counts the expected number of nodal domains. And of course, it's dominated by the allowed region. You're going to get you're going to get the right power of lambda just from the allowed region alone. So you're really only interested in what goes on in the forbidden region. Again, like how many nodal domains are there? Like we proved that the density of nodal set is square root in the forbidden region is the square root of the answer you get in the allowed region, much less density. So it also just looks from the pictures you get far fewer nodal domains. So I'm just wondering if that has been studied or not, if you happen to know any results like that.
No, I don't. I'm not aware of any of those.
Okay. Yeah. It's also, this is a long shot. It just is something that occurred to me during your talk. It's very hard to count the number of connected components of the nodal set intersected with the boundary of the allowed region. You know, how many of these nodal, or touch the boundary of a domain in higher dimensions than 2, or touch the boundary of the allowed region. But the volume has been calculated. We know how much the volume is for the intersection of, we know an upper bound for the volume of the nodal set intersected with the boundary of the domain or with the boundary of an allowed region. So I don't, see, that's a crude thing, cruder than knowing things like numbers of nodal domains, but it may be possible to use it, because you just get square root of the eigenvalue. That's the upper bound. You get this for any codimension, in fact.
Yeah, well, actually, maybe one remark. So basically, usually you have this phenomenon where the L2 norm of the eigenvalue will sort of like grow when you get close to the end of the classically allowed region. Like it oscillates, and then it oscillates slowly, but it goes up.
So say it again. You said the L2 norm of the eigenfunction, you mean?
Yeah.
Yeah, in a little like a collar neighborhood of the boundary of the allowed region, you're saying?
Yeah, well, in
that happens, I know, in dimension 1, but you have a kind of airy phenomenon that things have airy full singularities over the boundary of the allowed region. So there's a slight enhancement in dimension 1, but I'm not sure if that's even true in higher dimensions.
What I mean is that if that's also true, it means that our method to localize things close to the boundary would work really well. Because if something has a very high L2 norm, or it's like it sort of balloons over there, you can cut it and get estimates this way. Now, then again, there's a lot of waving in there, but it's sort of like that's the first thing I would think about.
Speaking of that, there are estimates on nodal volumes which require having a good notion of the L1 norm of the eigenfunction near the boundary of the allowed region.
Okay.
Have you ever seen L1 norms come up?
In our calculations or in other?
Yeah, in your work.
Not really.
No. Yeah. Okay.
Well, I mean, also our method by just dealing with L2 norms gave us what we wanted. So it's not like we were in need of dealing with other norms than L1 norms.
Yeah, it's just curious. L1 norms are kind of complicated for eigenfunctions, but they control things about the nodal volumes nearby the boundary of the allowed region.
Yes, I guess so.
Okay, thanks.
Thank you, Steve. Thank you, Philippe. Does anyone else want to comment or ask something to Philippe? If not, let's thank Philippe again. Thank you very much for the talk, Philippe. And next week, as Jean mentioned, there will be a break, and we will resume the seminar on October 18 with the talk by Daniel Stern. And please be aware that the talk will be 1 hour earlier than usual for that talk on October 18. Thank you very much, everyone, and have a great week and great following week. Bye-bye. Merci, Philippe.
Merci. Merci de l'invitation.
Ça fait plaisir.